Primary control. Primary control is defined as a control by confirming that the borehole pressure is greater than the formation pressure. It maintains a positive differential pressure or overbalance on the formation pressure. Based on the figure 5.3, as the drilling progresses, the formation pressure increases at a constant rate. But as it reaches the new formation, the pressure spikes at a high rate. In this case, the mud pressure should be higher than the formation pressure to avoid the occurrence of kick. This control may be misled to higher formation pressure than the wellbore pressure in two ways. The first reason, if the formation pressure is not correctly predicted. For instance, the reservoir engineers or geologists predicted that the formation pressure lower than the expected. As a result, the drilling engineer would have programmed a mud weight that was too low. Therefore, the bottom hole pressure would be less than the formation pressure. The second reason, if the pressure due to the column of mud decreases for some reason, and the bottom hole pressure drops below the formation pressure. Since the bottom hole pressure is a product of mud density and the height of column mud, therefore the pressure at the bottom of the borehole can only decrease if either the mud density or the height of column of mud decreases. Based on figure 5.4, as the drilling progressed, the drilling mud pressure exceeded the formation pressure or well under control. However, as it reaches the new formation, the formation pressure increases instantly, becomes higher than the wellbore pressure or loss of well control. Based on figure 5.5, as the drilling progresses, the pressure also increases, and the drilling mud is unable to surpass the formation pressure. These two figures can lead to a kick. There are different reasons for the reduction of mud weight and or the hydrostatic pressure of mud column under normal drilling operations. The following are few of those reasons. 1. Low mud weight. 2. Reduced height of mud column. 1. Low mud weight. There are many reasons that influence the mud weight. It may be too low due to A. An overpressured zone which may have been penetrated, requiring a heavier than normal mud weight. B. Gas cutting of the mud. C. Excessive dilution of the mud or water contamination. And D. Inaccurate measurement of fluid density. The normal industry practice is to keep the overbalanced pressure at around 200 to 300 psi. If there is a large amount of overbalance, the rate of penetration or ROP will be reduced, and as a result, cost of rate of penetration per time will be increased, which is an economic situation. If the mud weight is becoming less, the developed overbalance will be less, and hence the risk of having a kick increases. B. Solids removal. The cuttings must be removed from the formation to allow efficient drilling when the mud returns to the surface. If a very fine screen is used on the shell shaker, a large amount of waiting solids, especially barite, may also be removed. The screen size should be selected so that the shell shaker removes only the larger particles related to formation, while the inner material drops out and the sand drops. C. Dilution. When the mud is being treated to improve some property like viscosity, the first stage is to water back in order to lower the percentage of solids. Water may also be added when drilling deep wells where evaporation may be significant. During these operations, mud weight must be monitored carefully. 2. Reduced height of mud column. Under normal drilling operations, the volume of mud pumped into the borehole should be equal to the mud returned. In such case, when mud pump operations are stopped, there should not be any fluid flow from the well, and thus the level of mud pump should not fall below the mud pit level. However, this is not always the case. Reduction of mud pit level or mud column height may occur due to the following reasons: A. Dripping, B. Swabbing, and C. Lost circulation. A. Tripping. When the drill pipe is pulled from the borehole, during the tripping operation, the top of the mud column will fall down. This results in a reduction in the height of mud column above any point in the well bore, which creates a decrease in the bottom hole pressure. Therefore, the open hole must be filled up with pulling out of the hole, which is done by equivalent volume of drilling fluid. B. Swabbing is a process where the drill pipe acts like a piston. During the upward motion of drill pipe, it creates a region of low pressure into which formation fluids may flow. The opposite effect is known as surging, when the pipe is run into the hole. The amount of swabbing will increase with 1. The adhesion of mud to the drill pipe. 2. The speed at which the pipe is pulled. 3. Use of muds with high drill strength and viscosity. 4. Having small clearances between drill string and well bore. 5. Thick mud cake. 6. Inefficient cleaning of bit to remove cuttings. C. Lost circulation. This occurs when a fractured formation is being drilled. Whole mud is lost to the cavities in the rock, which reduces the height of mud in the borehole. Lost circulation can also occur if too high a mud weight is used and the fracture gradient is exceeded. Whatever the cause of lost circulation is the process by which the drill pipe acts like a piston. During the upward motion of drill pipe, it creates a region of low pressure into which formation fluids may flow. Warning signals of kicks. A blowout does not usually happen suddenly. While drilling, the crew must be watchful. They should know the warning signs at the surface and be able to understand the influx at the bottom of the borehole. An alert crew can see the warning signs, and if it is interpreted correctly, the well can be saved by immediate correct actions. Even though these signs may not necessarily always positively identify a kick, they do provide a warning and should be monitored carefully. Sometimes, the driller observes several indicators at the surface, which might be due to events other than an influx. As a result, the signs are not always final. For example, if the drill bit enters in an overpressure zone of a new formation, the rate of penetration will increase. It might be happen due to the new formation encountered by the bit. On the other hand, there are some indicators need to be monitored continuously to restrict having kick. Normally, there are two types of indicators: primary indicators and secondary indicators. Primary indicators. While drilling, there are some indicators that are more obvious than others and are therefore called primary indicators. The following are the primary indicators. 1. Flow rate increase. 2. Pit volume increase. 3. Flowing well with pump shut off. 4. A proper hole fill up during trips. 1. Flow rate increase. While the mud pumps are circulating at a constant rate, there should be a steady flow rate of mud returns to the mud tank or pit. If this flow rate increases without changing the pump speed, this is a sign that formation fluids are entering into the well bore and helping to move the contents of the annulus to the surface. Therefore, it is very important to monitor flow rate into and out of the well continuously using a differential flow meter. The meter measures the differential rate at which fluid is being pumped into the well and the rate at which it returns from the annulus along the flow line. 2. Pit volume increase. If the mud flow rate into and out of the well is constant, the volume of fluid in the mud pit should remain constant. A rise in the level of mud in the active pits is a sign that some mud has been displaced from the annulus by an influx of formation fluids. The level of the mud in the mud pits is therefore monitored continuously. 3. Flowing well with pump shut off. When the rig pumps are not in the operating condition, there should be no fluid returns from the well. If the pumps are in shutdown condition and the well continues to flow, then the fluid is being pushed out of the annulus by some other forces. In such case, it is assumed that the formation pressure is higher than the hydrostatic pressure due to the column of mud. This higher pressure results in an influx to the wellbore, which ultimately falls out to have a kick. There are two exceptions to this explanation. 1. The thermal expansion of mud in the borehole in annulus, which results in a small amount of flow when the pumps are shut off. 2. U-tubing effect when the mud in the drill string is heavier than the mud in annulus. A flow check is often carried out to confirm whether the well is kicking out or not. The procedure is as follows. 1. Pick up a Kelly until the tool joint clears the rotary table. 2. Shut down pumps. 3. Set sleeves. 4. Observe flow line. Check for flow from annulus. 5. If well is flowing, close BOP. If not flowing, resume drilling. 4. Improper hole fill up during trips. The hole should be required to be filled up with mud when the pipe is stripped out. If the hole is not being filled and does not take the calculated volume, the drill pipe volume, formation fluids, will replace the empty space. Secondary indicators. While drilling, there are some indicators that are not conclusive and may be due to other reasons. The following are the secondary indicators. 1. Changes in pump pressure. 2. Drilling break. 3. Gas, oil, or water cut mud. 4. Reduction in drill pipe weight. 1. Changes in pump pressure. An entry of formation fluids may cause the mud to flocculate and result in a slight increase in pump pressure. As flow continues, the lower density of the influx will cause a gradual drop in pump pressure. As the fluid in the annulus becomes lighter, the mud in the drill pipe will tend to fall and the pump speed will increase. 2. Drilling break. A drilling break is an abrupt increase in the rate of penetration. It should be treated with caution. If the drilling parameters have not been changed, the increased penetration rate may be attributed to A. Change from shale to sand, more porous and permeable, and so having a greater kick potential. B. Reduced overbalance or increase in pore pressure. The drilling break may indicate that a higher pressure formation has been entered. An increase in drilling rate may also be due to a change from one formation type to another. 3. Gas, oil, or water cut mud. Gas cut mud can be defined as the mud where an ingress of gas happens from formation while drilled. In reality, it is not possible to prevent any gas entrance to the mud column. Gas cut mud may be considered an early warning sign. The mud should be continuously monitored and any significant rise above the background level should be reported. Gas cutting may occur due to A. Drilling in a gas-bearing formation with a correct mud weight. B. Swabbing when making a connection or during trips. C. Influx due to negative pressure differential. The detection of gas in the mud does not necessarily mean the weight should be increased. The cause of the gas cutting should be investigated before the action is taken. 4. Reduction in drill pipe weight. The reduction in drill string weight happens when a substantial influx occurs from a zone of high productivity. However, the other indicators may be displayed prior to or along with a reduction in drill pipe weight. During the operation, it is not essential to close valves inside the drill pipe since the drill pipe is connected to the mud pumps. This allows controlling the pressure to the drill pipe. Generally, it is required to close the uppermost annular preventer like high drill. However, the lower pipe rams can also be used as a backup if required. The surface and annulus pressure should be monitored carefully. The pressures can also be used to identify the nature of the influx and calculate the mud weight required to kill the well.
Secondary well control. Let me first explain that if there is a pit gain observed at the surface, it means that the kick has been identified by the drilling personnel. This pit gain indicates that the primary control over the well has been lost. In such a situation, all normal drilling or tripping operation must be terminated in order to concentrate on bringing back the well back to primary control. Secondary well control. When primary well control is failed, it causes kick or wellbore influx coming into a wellbore. Therefore, this situation needs special equipment, which is called BOP or the blowout preventer, to control kick. The purposes of this control are, first, to stop the flow of unexpected fluids into the wellbore. Second, to allow the influx to be circulated to the surface and safely discharged. Third, to prevent further influx to the downhole. We also have steps for secondary control. Step 1 is to close the annulus space at the surface with the help of BOP valve to prevent further influx of the unexpected formation fluid. Figure 5.6 shows the secondary control system and its pressure rating. Step 2 is to circulate the heavy mud through the drill string and annulus to displace the influx and original mud. Step 3 is to allow the drilling mud with a control way so that no further influx occurs at the bottom of the borehole. In such case, the heavier mud should prevent further influx of formation fluid when drilling ahead, which is now under primary control. Secondary control is only required in drilling exploration wells where formation pressures may not be known. Well killing procedure. The first method, claiming to be the simplest and most effective technique for controlling kicks and should be used anytime a formation fluid influx is circulated out of the well, is drill pipe pressure method. This method does not require that the volume or type of feed-in fluid must be known and works equally well for gas, oil, and water kicks. The kill procedure is summarized as follows. 1. Pick up Kelly until tool joint is above rotary table. 2. Shut down pump and check for flow. 3. Close annular BOP. 4. Close adjustable choke. 5. Record shot in drill pipe and casing pressures, pit volume gain, depth, and original mud weight. The drill pipe float normally has a small port to transmit pressure to surface. If non-ported drill pipe float is used, the pressure to pump the float value open should be used as the drill pipe pressure. 6. Determine the circulating drill pipe pressure. This can be done by holding the casing pressure constant at the shut-in value and pumping down the drill pipe at constant and reduced rate of 0.5 to 2.5 bpm. As the pump starts, the casing pressure tends to increase. Choke on the annulus is manipulated to keep its pressure at constant, and by holding it by a required time, it will bring to a pump to a desired speed. Read and record the drill pipe circulating pressure with the pump running at the desired constant speed and the casing pressure maintained constant at the shut-in value. The bottom hole pressure is common to both annulus and drill pipe, and is being held at a constant by holding the casing pressure constant. This is true as long as the pump rate and mud weight remains the same. The difference between the shut-in and pumping drill pipe pressure is that the pressure necessarily to cause the mud to circulate at a desired rate. Changes in drill pipe pressures due to choke manipulation will usually require approximately 2 seconds for 1,000 feet of well depth to register on the standpipe gauge. However, this lag-in response time can be longer if the mud is contaminated or a large gasket is present. 7. Once the drill pipe circulating pressure becomes stabilized at a desired casing pressure, hold the drill pipe pressure constant by adjusting the annulus choke. Continue to pump originally mud at the same constant rate and circulate out of the kick to surface. 8. Pump kill mud of heavier density to the bit. Make downward correction in the drill pipe pressure as described in the following section. 9. Continue circulating at constant pumping rate until the mud of the required density to kill the well occupies the wellbore. And last, stop circulation and check for flow. In the above procedure, the kick is circulated out in step number 7 using the original mud weight, and then kill mud is circulated to kill the well. This approach of weighting up the mud is called driller's method, and it offers the advantages of relative speed and simplicity, but generally results in a higher maximum surface pressure than other methods. If the sufficient barrette is on hand to weight up the mud, this method should be used rather than suspending operation until barrette can be delivered. If sufficient barrette is available on the well site, step number 7 may be deleted, and then well killed by circulating kill mud as in step number 8. This method of weighting up the mud called the weight and weight method. It will result in lower surface casing pressures and requires less time since the well is killed in one circulation. The drill pipe pumping pressure should be adjusted to correct for the increase in hydrostatic pressure and friction pressure losses as a result of pumping the heavier kill mud. The pressure of adjusting the drill pipe circulating pressure is described in the following section. I will be showing you guys a clip of the driller's method and weight on weight method.
Let's see this illustration for driller's method of well kill procedure. The smaller leg in the illustration represents the drill pipe, and the bigger leg represents annulus. The diagram shows a gas kick and the well is shut in. The driller records the initial shut-in drill pipe pressure and shut-in casing pressure. The pressure needs to be stabilized before the final readings are recorded. After recording the SIDPP and SICP, the driller initiates the first circulation, which is with the original mud that is present in the well to circulate the influx out. At the end of first circulation, the influx is out of hole, and, at this stage, SICP equals SIDPP, to confirm that the kick has been circulated out and no more gas is in the well. At this point, the driller lines up to circulate the kill mud. In wait and wait method, normally, only one circulation is needed to kill the well.
Blowout prevention equipment. A blowout preventer, or pronounced as BOP, is a specialized valve or similar mechanical device used to seal, control, and monitor oil and gas wells to prevent blowouts or the uncontrolled release of crude oil or natural gas from a well. They are usually installed in stacks of other valves. Blowouts are a particular hazard offshore because not only they are danger to life and limb, but in the case of any oil blowout, they also generate an oil leak and much unfavorable in publicity. The majority of blowouts, however, results from the sudden release of gas or the uncontrolled release of crude oil from the well after pressure control systems have failed. Blowout prevention. Nowadays, companies use blowout prevention equipment at the drilling site in case of a bad kick or a high upward pressure formed by the fluid surging up the well. To maintain the pressure balance, drilling engineers use drilling mud to maintain equilibrium between the upward and downward pressure to avoid any breaches in valves that can lead to overflow of energy resource causing severe damage. But what is the role of BOPs or blowout prevention equipments in drilling operations? BOPs plays a crucial role in oil drilling. While most individuals understand what is the basic functions of this device, but that is not enough. There is a need to understand each component of BOPs, their individual functions, and how they work together in order for increased safety and efficiency. Taking a look at the basic components of every BOP, first we have accumulator. The accumulator is the main control unit of a blowout preventer. It is responsible for the control of all systems that interconnect in preventing emergency situations. It is activated based on hydraulic pressure. The accumulator houses hydraulic reservoirs, control valves, pumps, control manifold, and compressed gas bottles, among other features. And also we have annular BOP. The annular BOP is responsible for closing the space around the drill pipe. It does this by controlling the airflow to prevent mud, without affecting the operation of the system. It is effective in maintaining a seal around the drill pipe during the process of drilling. Annular BOP is on top of the other BOPs to ensure efficient airflow control. Next is RAM BOP. The basic function of the RAM BOP is to prevent unwanted materials from exploding in the system during drilling. Several RAM BOPs perform other functions to ensure safety. Some of them are blind rams, which closes over any portion without a drill string. Choke manifolds. This is a system of a pressure sensors which controls the flow of fluids in various direction. And the next is kill line valve. This acts as backup to the standard drill pipe. Blowout prevention equipment structure. As you can see in the picture, here is the structure of blowout prevention equipment. We have aluminum thread protectors, carbide ball sets for superior sealing and equalizing, and bleed-off bulbs, bleed-off or grease injection manifold, bumpers to protect BOP's bulbs and body, invertible rams to suit operations, monoblock forging, easily accessible equalizing and bleed-off bulbs, durable powder coat or painted finish available, external piston indicator, manual backup actuators, hydraulic actuator sliding arms to serve or replace rams, hydraulic actuator lock designed to allow quick and easy access to rams, and integrated lifting points. Blowout preventer. Blowout preventers are the final foolproof measure to contain the blowout in case there is a severe kick from the well. BOPs essentially shut down the fluid supply to and from the well in the final ditch to save a kick from turning into a blowout. And finally, here how it works, the BOP equipment and drilling rig, as you can see in the picture.
BOP stock arrangement. A BOP stock is several blowout preventers connected together one on top of the other. An example is, in a multiple ram configuration, one set of rams might be fitted to close on 5 inches diameter drill pipe, another set configured for 4.5 inches drill pipe, a third fitted with the blind rams to close on the open hole, and fourth fitted with a shear ram that can cut and hang off the drill pipe as a last resort. To further discuss this, a common BOP stock arrangement: first is annular preventer, next is blind ram preventer, next is pipe ram preventer, drilling spool, this is optional, also known as drilling cross, kill line, choke line, and fill line, lastly is bell nipple. There are several considerations on how to arrange a BOP stock. First is BOP stock must be suitable for the drilling operation. The stock should be able to serve the stripping operation, not just only shut the well in. Pressure rating must be higher than expected surface pressure and surface when the well control situation is happened. Excessive BOP rams cause difficulty to handle and maintenance. Additionally, the cost of BOP stock is more expensive. Sour gas and temperature and surface directly affects the element in the BOPs. The best BOP stock arrangement is the one that is suited for the operation within safety limit. Here we have an example of a convenient method of designation. 5M-13-5/8-RSRA. It indicates in order the working pressure 5000 psi, minimum bore 13-5/8 inches. The arrangement of the stock from bottom to top is RSRA, R for ram type preventer, blind or pipe rams, S drilling spool, A annular preventer, and other designations such as RD double ram type preventer, G for rotary stripper head for gas, air, or aerated fluid drilling. Assuming that the BOP stock has pressure and that there are no problems with the well such as lost circulation or a hole in the drill string. These are the activities that should be possible by the stock operation. Number 1 is normal kill down drill pipe using either pipe ram. Number 2, kill with blind ram closed. This option is required normally for ram, annular, or piping repair. The pipe is hung off on the lower pipe rams and the pipe is disconnected. The blind rams are closed and the kill circulation operation can be suspended, or it can continue while repairs are made in order to disconnect the drill pipe as shown. There must be a float in the drill string or kill weight must be in the drill pipe. Next is ram to ram stripping. This option is required to be able to get the drill pipe in or out the hole. Normally, when a well kicks while tripping, the requirement is to get back to the bottom or as close as possible to make the kill easier to accomplish. The stripping operation is called ram to ram stripping, but if the annulus pressure is not too high, the annular preventer and the top pipe ram be used to strip back to the hole, because if the lower pipe ram is damaged, there is no method to repair it. One of the pipe ram preventer would be different size or variable length for the drill strippers to impact. This is an example of stocks with 2 ram type preventer. This is from Saudi Aramco Class B 3000 PSI BOP stock. Where only 2 sets of rams are used, there are 4 arrangements for the blowout preventer stock as shown to the next. The discussion assumes the well is under pressure. There are a number of advantages for this stock arrangement. To drill pipe in the hole, the upper rams may be changed to the pipe rams. When this is done, the drill pipe may be reciprocated for the upper rams while maintaining the lower rams as a reserve. This is applicable for number 1 and 2. The two pipe ramps and some pipe in the hole, the drill pipe can be stripped back to the bottom. This is applicable for number 1. If a leak develops above the rotary, the drill pipe may be suspended in the lower ramps, and by closing the upper blind ramps, the hole can be circulated. This is for number 1. Also, this holds for number 2. There is sufficient distance between ramps to place tool joint box. Since most kicks occur with some pipe in the hole, the lower pipe ramps may be closed for repairs with drilling spool or flow line. This is applicable for number 1. When blind ramps are closed, these permit use of the drilling spool, flow lines, and chokes. Applicable for number 1, 2, and 3. With either of the ramps closed, this permit the use of the choke, flow lines, and chokes. Applicable for number 2 and 3. The application of the double type preventer allows substructure height may be used. This is especially so the outlets of the preventer are used in the line of the drilling spool. Applicable for number 2 and 3. Drill pipe ramps can be changed to casing ramps while the drill pipe is out of the hole for 3 and 4. If any serious leak develops in the stock, the drill pipe can be set on the bottom or dropped and the well closed in as a last resort. For number 4, there are minimum number of flanges exposed below the blind ramps. When the pipe ramps are closed, the choke line is available for use. This is applicable for 2, 3, and 4. When the blind ramps are closed, all of the previous connection can be stripped off or repaired. This is applicable for number 4. There are also primary disadvantages for this stock arrangement. If the blind ramps are closed, there would be no control if a leak occurred around the drilling spool. This is for 1, 2, and 3. There are more flanges exposed to the well pressure. This is for number 2 and 3. With bottoms ramps closed, circulation involved secondary casing head connection. This is for number 1 and 4. Flanges are considered weak points in any hookup. Therefore, where side outlets are used, number 2 and 3 are not considered the best arrangement by many because the drilling spool introduces an extra flange. Double ram units can be specially ordered with enough room between rams to hang off and shear. This special height double ram unit could be put on bottom, best satisfying both single and tapered string application. About stocks with 3 ram type preventers, a generally accepted configuration will be developed for a string with 1 pipe size and also for a tapered string. Here is an example of a stock arrangement and the possible activities for it. For normal keel down drill pipe using either pipe ram, there must be choke flow lines 2C and 3C below each pipe ram. For keel with blind or shear ram closed, a double ram unit must be on top of single ram to provide sufficient space for hang off and shear. Keel flow line 2K and choke flow lines 3C must be arranged as shown. For ram to ram stripping, as shown in figure 15 in this figure, blind ram must be in the middle to provide sufficient space with some models. Keel flow line 2K to equalize pressure before opening bottom ram. Choke flow lines 2C and 3C to bleed fluid and monitor pressure below each ram during stripping. Keel flow line 3K to lubricating fluid or keel below bottom ram. Would also strip between annular and either ram and do items 2, 3, 4 above. For location of blind ram in the middle, you must have more room for ram to ram stripping as previously mentioned, safe out of hole top ram change, annular element change or repairs to the single ram unit or annular. Note that this location of primary choke flow line 2C at alternate location 1C will allow all previously mentioned activities but is somewhat more exposed to mechanical damage. To conclude, the configuration of stock preventer is optimized to provide maximum pressure integrity, safety, and flexibility in the event of an accident. Do to keep in mind that the BOP stock is able to shut the well in and allow it to perform both full operation with the greatest flexibility.